what you're looking at on screen is a force curve for a bow. Two different bows, actually. The blue dots represent this Asiatic horse bow, laminated fiberglass. And the white dots represent this American style hickory flatbow. So we're gonna learn exactly how much energy is being stored in these limbs, how much kinetic energy will be imparted to the arrow in flight, and how efficient are these things really. Let's do the math. This bow is from Ali Bow. It's called the Zhongwu, and it is rated by the factory as 28, hard to read this, 28 inches, 40 pounds, or 35 inches, 55 pounds. This thing, I used stuff through too. This was designed to be about 55 pounds at 28 inches, which is, of course, a much heavier draw weight. It's made out of hickory with a lamination of hickory on the back. You can kind of see two different layers there. And I think it has a walnut handle and tips. All right, this is a device that I built to measure the draw force of these bows. And the brace height here is 20 centimeters. So let's start weighing it. I like to weigh every 2 centimeters. So we got a reading, 22 is 15 newtons. Try to get this lined up a little bit more. There we go. And we'll read it. I've already done all these, but 24, 31 newtons, 30 centimeters, 64. And we can crank it all the way to its maximum draw. Be so careful here not to break it. This will go to 87. $251 newtons. There we go. 250 newtons. Okay. All right, and the hickory bow is 71 centimeters, 238 newtons. There you go. This is the arrow we'll be shooting with the horse bow. It is 50 grams, and the length is, line up the nock with the end of the board. The length is, let's see here, there we go, 85, 86, 87 to about right here on the point, which is how far I draw. This is the arrow that we're using with the hickory bow. The mass is 37. And the length is 71 to about right here, maybe 72 if you drew all the way to, there we go, 72 if you drew all the way to the max.
Sometime next year.
58, 58. Okay. 44. 46. Do one more. 46. We have gathered all our data. Let's put everything together and do the math. Here we have, for the Ali Bow Zhongwu, the force draw data. So here we have centimeters from back. Brace height is 20. We draw it all the way to 87. And here we have my recordings. We get a chart that looks like this. And I also added a straight line to show what a linear path would look like. Let's do the same thing for the hickory bow. It looks like this. You can see that the draw curve of a flat bow is very linear. It's a little bit aggressive at the beginning and a little bit low at the end, and it starts to stack here at the very end, but quite linear. This one is much more interesting. The reflex on the bow means that you can start storing energy much earlier. It feels very hard at the beginning. When you put these together, you can see um, the the horsebow actually starts out harder to draw for the first third of the draw or so, and then it's easier to draw toward the end. So overall, this bow feels much nicer to draw. Also, it's a lot. You're a lot stronger at 85 centimeters than you are at 70. So even though they have a similar draw force here, trying to draw a heavy bow to your mouth is using the weakest muscles, and you're going to get, you're not engaging all of your strength, and then what we want to do is we want to integrate all the area under this curve to find out how much energy is being stored. And that sounds like it would involve calculus, but it's actually very simple, because we already have the numbers all in front of us. Each increment, this number represents the force we had to expend, or the force we had to exert to increase the distance by that increment. These are 1 centimeter increments. So, for example, to go from 27 to 28, we had to exert 52 newtons of force. All we have to do is multiply 52 newtons times 1 centimeter. So we divide that by 100 and we get Newton meters. Here we did 1 Newton meter of work. Here we did a bit more than 1, right? So we add all these up, basically. We just sum this column, and we sum that column, and we divide by 100, and we get the work expended to draw this bow, which is 93 joules. 93 Newton meters of work. And because of the work energy equivalence, we can say that it's also equivalent to 93 joules. And again, that's the area under this curve is 93 joules. Let's see. Another very, very sort of quick math way, if you wanted to find the area under this trend line, you would simply divide the final number, which is 250, by the distance, which is 65 centimeters, 67. So equals 250 times 67 times 0.01 times half, because it's a triangle, times 0.5. And you get 83.75. So the area under this trend line is 83.75. Our bow does better than that because it has this aggressive curve here. So we're going to get, our boa is doing better than the trend line because of the reflexes, basically. Okay. We weighed our arrow, 50 grams. We clocked it at 58 meters per second. That gives us a kinetic energy of, here you go, 1/2 times speed times mass divided by 1,000, because the mass is in grams, we need kilograms, and that gives us 84 joules. You divide 84 by 92, and you get 90.7%. This bow is 90.7% efficient. Not all of the energy that you spend to draw this bow ends up in the arrow. Most of it does. Where does the rest go? Noise, hand shock, heat, wind resistance. I'm not sure. I've also tested with a heavier arrow. So with a 63 gram arrow, it was 52 meters per second. That gives us slightly more energy and slightly higher efficiency. If you used a very heavy arrow, you could approach 100% efficiency, but I prefer this arrow. This arrow gives a nice speed. You lose utility with an arrow that's so heavy that it won't travel very far or very fast. So I think this is a nice balance for this bow, 91% efficient. The hickory bow, we did the same thing. It's actually doing about equal. It's such a linear draw curve that it probably does very equal with its trend line. In fact, we can do the math here. We drew this 51 centimeters times 238 times 0.5 times 0.01, 60.69 joules. It says here we stored 61.2. So it's doing a bit better. than the trend line. Somehow, actually, doesn't visually look like that, but okay. Let's see, arrow was 37, arrow speed was 46. That gives us a 39 joules. We divide that by the work we expended and gives a 64% efficiency. It's not as efficient. Maybe we should have made the bow narrower and thicker. Maybe we should just, the laminations make a bow more efficient. So this is just a chunk of wood. Fiberglass is going to do better because it's on the belly and back. So yeah, there's a lot of technology in this bow that makes it more efficient. You could say we could use a heavier arrow to get more efficiency here, but I'm not really comfortable going much below this speed of arrow speed. That's already pretty slow. All right, and again, looking at them together, that is the end of our math.